Hi guys, welcome to our channel of Sciences and Mathematics. I'm Ernest. Today we're going to look at one of the major areas in vector calculus, and that is the derivative of vectors. In one of our videos that I'm going to put a link in the description box, we have discussed the concept of integration of vectors. And we said together with this derivative of vectors, they find wide application in several areas, of course, like gravitational fields, the control system, fluid dynamics, and electromagnetism, and maybe in structural analysis. So as we have talked about that specific area for their relevance, I'm going to also use some of the areas that you have done in elementary derivatives or maybe calculus in order to find the derivatives of vectors, just as we did for integration of vectors. Now for this case, we're going to define maybe a derivative in terms of those vectors and try to use an example in order to solve maybe one problem or two. So without further ado, thank you and welcome. So as I've said, we're going to look at the derivative of vectors. And as we said, they already defined that for maybe if we have a scalar variable u, set for that. For a scalar variable u, or maybe if we have a scalar variable u, then we can be able to find and if it contains a corresponding vector au, then we can be able to define that vector as a vector function of u, which we had written as au. And this vector function is going to assist us to define derivative of au, which can be given as dA over du. It's going to be given as a into u plus change in u. This is just analogous to the normal derivative that we write, but we're going to use that vector function of u in order to define it. So the change in u. So this is basically the limit of this function as change in u tends to 0. So basically this gives a general representation for this vector function, derivative of this vector function. Now, provided that this limit exists, when we were trying to talk about the concept of maybe continuous functions or maybe a differentiable functions, we talked about the concept of a limit. So in this case, if a limit exists, therefore that function is differentiable, we can be able to write the components of this vector function u as a1, a2, a3. So this is going to be au, the I direction, au, j, au. Okay, so this vector function of a can be represented using those specific vectors. Therefore, as we have defined the derivative for this specific function, therefore we can have a general representation for dA du represented as, so the dA1 over du plus dA2 over du plus dA3 over du. Of course, these are represented with their specific j and k elements of those specific vectors. Now we're going to see maybe specific cases for higher derivatives, but in this case we're going to just restrict ourselves to this specific definition from this general concept of a derivative. So we're going to use an example in order to try and figure out how we can be able to find this specific derivative of vectors. But before we do that, we're going to have maybe a general representation for some of the vectors that we may come across. And in any case, of course, there's a different notation that we can be able to use for representing this derivative of vectors, or maybe generally a derivative, and we're shortly going to look into that. Now, as we said, we can be able to represent a derivative, represent a derivative of r with respect to t. Now, in kinematics, this basically indicates the concept of velocity, but we're going to represent this one as r using that specific dot, and this basically implies the first derivative. And if we represent the second derivative of r with respect to t, so this is going to be represented as r with those two specific dots, and this is the second derivative. So in any case, if we do a representation for these two specific derivatives, we can be able to use the dots in place of symbols to denote the derivatives of the first and the second with respect of the first and the second of r with respect to time. Now there are also other general representations that we're going to use in order to define these derivatives, or maybe general representations that we can use in order to show how we can be able to find derivatives. Now that we have given a general representation for the derivative, now suppose we have a function, or maybe a derivative of this function of a with respect to u. Now the derivative of phi a du is going to be given as phi dA over du plus the derivative of phi du a. So this is one of the rules that are going to be applicable on this. Now suppose we have a derivative of dot product AB with respect to u, then this is going to be represented as a dot b with respect to u plus dA dot dA du dot b, and then lastly we have a function of a gross product with respect to u. So basically we're trying to represent vectors. Here we can be able to find the derivative of vectors. We're going to have a, the gross of dB with respect to u du, and then plus dA du cross b. So this is a general representation for the vectors that we may come across and how we're going to perform their derivative for dot product, and this is a general representation for phi a. And basically I hope that we're going to remember that, so we can proceed and try to give our example so that we can be able to see how we can perform a calculation for derivative of vectors. Now if a is a vector that can be represented as a is equals, just have a space here, a is equals 2u cubed minus 3u for I plus 5 the cosine of u, this is for j, minus 3 the sine of u, and this is for k. So these are just a representation for vectors. So therefore if we were asked to find dA du, which is basically a derivative of that function, and this is going to be, so this is a u2 over, so basically this is going to form a, so this something I just, it's a little bit of confusion. This is a u squared, so therefore we're going to have 4u minus 3, this is for I, and then plus 5. The derivative for trigonometric function cosine is going to give us the sine of u, j, minus the derivative of the sine function is going to give us the cosine of u, k. So that basically is going to give us a derivative for that specific function for the I, j, and k respectively. So suppose we had a second derivative for this specific function, then we're going to have this one represented as 4i plus 5. So this is going to change into the cosine of uj minus 3 the sine of uk. So that's for the second derivative of that specific function. So basically we're going to see that this operation for the derivatives of functions for integral, for vector calculus, is basically follows the normal, or is analogous to the elementary calculus that we perform, only that we have to be very keen in trying to represent these specific components that we have already defined. So in this case, I hope that given a derivative of a function, maybe of a vector function, that the one that we have represented maybe for a and r, and other arbitrary function that we will come across, it will be easier for us to try and do a representation, maybe in finding that specific vector as I've done on the board. So I hope, guys, that you continue to subscribe to our channel, and also follow us on the social media, since we are also posting some of our contents there, so that we can be able to have maybe a healthy discussion and find out how we can be able to assist one another and solve maybe problems and develop other skills which are basically going to assist us maybe have a hand in both sciences and mathematics. So basically that is for today, guys. Bye. God bless you.